what was called the nightmare scenario was at LHC you find nothing but Higgs plus nothing. So this was typically called as the nightmare scenario, but you wouldn't expect anything else other than the Higgs. Then all the naturalness arguments, all the models which we built for, dark matter, explaining dark matter or explaining grand unification, everything completely collapses essentially. Okay, and this is exactly what happened. Okay, so this is precisely, this was called the nightmare scenario, and people used to think that no, there will be something. They were always hopeful. Essentially, they will be saying that, okay, they'll find something. Of course, they'll find something. They'll find something. Nothing came out. This was say right from 2000 to all the 2020s and up to 2012. Okay, beyond 2012 also people expected a little bit of Higgs, but nothing. Beyond something else they'll find, but nothing came out essentially. So this was the expectation till 2010s. Why did they call the nightmare scenario? Okay, the Higgs was discovered with mh square around 125 Joules square. And in most models, so there is a history behind this. In most models, you can actually estimate what is the Higgs mass. So even though the Higgs mass was not computable in the standard model, in many models you can actually compute it. Okay, or estimate it pretty well essentially. One of the simplest, okay, what I'll do is I'll just give you some formulas, okay, which will tell you what is the expectation of the Higgs mass. And what happens is, in all these models, while you estimate the Higgs mass, which comes around 100 GeV, say, okay, it automatically insists that there should be some partners of the new physics which are at about a TeV. In all the most 90% of the models it happens. Okay, 90% of the model it happens. Around a TeV, 1 TeV, 2 TeV, as long as they satisfy natural. So I will do a more detailed analysis later on, the structure, mathematical structure and everything. But today, because I'll be just to give you a grip, meaning there will be some loose ends, there will be a lot of loose ends for what I'm saying so far. But what I'm, since today we are going towards understanding the Higgs and the LHC results. So what I'll do is I'll just mention what is the expectations based on supersymmetry, say for example. Then I'll talk about extra dimensions, then talk about composite Higgs. So expectations. MSSM is minimal supersymmetric standard model. Okay, MSSM. In this model, the Higgs mass is equivalent to mz square at the tree level. It's a prediction. So the lightest Higgs mass is predicted to be 91 Joules square plus or minus some factor order 1 essentially, where tan beta is is equal to V2 by V1, and accordingly you can define what is cos square beta essentially. Now, obviously, this is ruled out, right? 91 Jev Higgs is ruled out. But what happens is it has an extremely large one loop correction. So, extremely large one loop correction, which goes as from 3hd square. Roughly like this. There is an A term also, and so on. So now, if you look at this, this is a very, very large contribution because it goes with ht square. Okay, should be dimension correct. Okay, so this goes as ht square. So that means this itself will add 30-40 Jev to the mass of the Higgs. Now, assuming the stop masses to be around 1 TeV or so, okay, below 1 TeV, you can put an upper bound on the Higgs mass, okay, for stop masses. This is top, okay, this is supersymmetric partners of top, which I put with a tilde on the top. So this is the top mass, this is stop masses. These are called stops. In supersymmetry, every fermion has a scalar partner which is called stop, okay, and every fermion, every scalar has a fermionic partner which is called eno. Okay, there's something called Higgs eno. Top has a stop, okay, of the standard model. So this is the stop masses. Now, instead of calling it as stop 1, stop 2 square, we'll just call it as typical SUSY scale. Okay, we'll just call it as some typical SUSY scale, SUSY mass square. T1 are they mix actually. Top 1 and top 2 mix. Stop left and stop right mix, and they form two eigenvalues which are called T1 and T2. Their mixing can be very large. So let's just say that this is of the order of m SUSY square by m top square, and this itself can give you a pretty large, not only logarithmic factor but also this essentially. Okay, so some 30-40 GeV will get essentially, you'll get just from this. And now you can say that if there is a mixing, you can maximize this thing. Okay, assuming maximizing it, m SUSY around 1 TeV. Maximizing m SUSY around 1 TeV, you will end up having a Higgs mass upper bound about 135 J. But this requires at least one stop, one of the top partners to be around 1 TeV. Did we find it? No. Stops are colored. Okay, stops are colored particles essentially. They are produced typically, you can say, okay, they are very hard to produce in PP colliders because they have to be produced through tops, because you cannot produce them by any other way essentially. So, and they can decay to tops. You produce them by gluinos or gluons and everything, and you produce them in stops and everything. So typically you can imagine pair production of a gluino or a single the production of a gluino going into a top and then a stop, and this stop itself will decay into a top and something else. So you need even kinematic energy with these at least two tops to be formed essentially. There are configurations of Feynman diagrams where you can think of at least one top should be there. Okay, so if you put some other glue, this could make it virtual, and then you can make it stop. So in the end, you'll end up having at least one top. So you can look at all the single top events or two tops events or multiple top events and everything at LHC, and then put constraints on this particular thing. And we have so far not found anything around a TeV. The present constraints are much larger. You can go to Twiki dot okay, one of these Twikis of CMS. I'll show you this plot. Okay, just type Twiki CMS or Atlas in Google, and you'll find the page, and you'll find the latest experimental bounds on supersymmetric partners and everything. Okay. So to summarize, first, the Higgs mass is computable in supersymmetry. It is a predictable in MSSM, and its mass tells you that it is at tree level is just mz square. But one loop corrections can be very large depending upon the stop masses. And if we have a Higgs mass which is very light, according to supersymmetry, it's light because it's below 135 GeV. It's 125 GeV square. That typically requires at least one of the top partners to be less than 1 TeV. But did we find? We didn't find. We didn't. And this calculation has been refined. So now there are 2 loop corrections, 3 loop corrections. At 2 loop there are gluino corrections which are negative in direction. Then you can ask the question, suppose if I have 2 loop corrections and with a heavy gluino, maybe there could be negative corrections. Okay, even putting all the super 3, then there are leading order 3 loop corrections in supersymmetry to predict the Higgs mass. So this number, this 125 GeV, what is discovered, where is this? This one is the biggest constraint on supersymmetric theories, because supersymmetric theories you can calculate this number. You can calculate this number and all the parameters can be predicted and estimated, and you don't find anything at LHC. So, even then it cannot escape much. Okay. So even if you have NMSSM, the point is that the discovery of the lightest Higgs should always, CP even Higgs, cannot have lot of single component. So it should be almost like a Higgs, standard model Higgs. So that puts a constraint that you cannot raise it by other contributions. You are right that suppose if you have an NMSSM, then there will be a lambdas, some s square, some other contribution comes in. Okay, but this contribution should be highly suppressed. Something is there, I forget the exact expression, but there is an expression in NMSSM which is proportional to lambda and everything. Here also maybe some other cos beta or some combination sin 2 beta or something will come. Now this contribution should be suppressed because the lightest particle should be almost like a SM Higgs. The single component of it should be very small. That comes from the eigenvectors, not from the eigenvalues. Okay, that's because we have seen the Higgs coupling to ZZ, Higgs coupling to WW, so it should be almost same as the Higgs. So what he is arguing is that suppose if I modify the MSSM with some other, adding a singlet Higgs or something, essentially, okay, then the tree level relation will change by some higher component essentially. But this won't be sufficient actually. This itself has a very strong constraints. You can explain the data. I'm not saying you cannot explain the data and everything, but still you would need heavy particles which are close to TeV or something. It's not ruled out, but already people are getting very fidgety and everything. Now if you ask me, is it completely ruled out? No. Okay, I'll still some parameter space will be there, which you can play around with and everything. The only thing which is ruled out is one particular model of uh, supersymmetric braking, which is called gauge mediation supersymmetric. Okay, which doesn't generate trilinear couplings. Okay, it generate its prediction is trilinear couplings are zero essentially. But this one, anything which generates trilinear couplings is still allowed. Okay, is still allowed, and you see that already it's not completely 100% ruled out. No, you can play around a little bit with the parameters, squeeze it, but it's super fine tuned. Okay, it's super fine tuned, and this number puts extremely strong constraints. In the simplest models of supersymmetry braking, this pushes the SUSY braking scale. It's called minimal supergravity. It pushes the SUSY braking scale to around 50 TeV, 100 TeV or something. So there is no longer a weak scale. So in minimal supergravity, the number M0 is roughly around 50 to 100 TeV. And M1 half, these are the parameters. This itself is about 8 to 10 TeV. That's because of the gluino mass essentially. No, sorry. More than 1.2 TeV or something. 1.2 TeV or something. From the gluino mass constraint. So what is happening is the gluino there are constraints on not only the colored partners, the colored partners enter the loop to the Higgs mass, and these color partners are not discovered at LHC because LHC is essentially a machine which can see colored particles, because it is just proton on proton. It can see all colored particles essentially, gluinos, stops, all colored particles essentially. So this is one of the reasons why this is called a nightmare scenario. Essentially, this falls back into the nightmare scenario. So if there are bets on various BSM models, the highest bet was on supersymmetry, and the next was on extra dimensions, and next was on composite Higgs, and the next was on. So the maximum amount of bets were on supersymmetry. Okay, and they expected to find at least one gluino or one stop or one of the colored particles essentially at the LHC. Gluinos were the main thing essentially. If you have found a gluino, that would have made life easier. Whether it's natural or unnatural, it doesn't matter essentially. You should find one colored particle so that you can explain your Higgs and live with it essentially. Okay, even if you modify and everything, the models started becoming no longer simpler models. They started becoming extremely baroque. And even if you make them, you can only make them satisfy the constraints of LHC. You can make them work. First of all, they are still not a natural. Okay, the models are extremely baroque, and it is like you can make SUSY survive definitely. Okay, but it doesn't have the original appeal as what was existing essentially. Okay, so SUSY says that there should be some extra particles. So extra particles, and they have not been seen. So these are extra. The extra particles are gluino and stop, colored partners not seen. So we are end up in the nightmare scenario. The second one, the in SUSY always it's logarithmic because it protects the Higgs mass. Okay, there are no quadratic corrections. Now all the quadratic divergences are cancelled. V1 square plus V2 square. So you can put V2 square if you want to be more explicit. 3 is the color factor and HT square is the coupling. Now let's look at extra dimensions. Okay. Today I won't go into the details. Like I said, I'll give you a flavor. Okay. Because why they didn't. So essentially, what we are looking at are why this particular discovery killed a lot of BSM models at one shot. Okay. Just discovering the Higgs killed a lot of BSM models and put significant constraints. So that is the power of an experiment. Okay, theorists can do whatever they want, but okay. Yeah, you cannot argue with an experimentalist. You see, that's the point. So one of the most popular extra dimensional models, which got immediately ruled out, are called the Higgsless models. Higgsless models. Okay, I'll just give you some ideas. So extra dimensions have something called x mu and an extra parameter y essentially. So x mu is your standard 4 dimensions and y is your extra parameter essentially. So this cannot be from minus infinity to plus infinity. This will be compacted on a circle essentially. So this extra dimension is a compact extra dimension. We will see this more detail later on stage if needed to be. So it goes back to a circle and that won't be sufficient in 5 dimensions. So if you write Dirac equation in 5 dimensions, if you are Lorentz group representation in 5 dimensions, you cannot have chiral fermions because you cannot define gamma phi. Okay, you don't have an independent gamma phi. Okay, you don't have an independent gamma phi. So there are gamma matrices. You need gamma phi independent, right? Essentially, you need to get gamma phi as a product of gamma 1, gamma 2, gamma 3, gamma. You won't be able to get that essentially. So for that, to get chiral fermions, you need to do something called orbifolding, where you break the 5-dimensional Lorentz invariance. You break the 5-dimensional Lorentz invariance at some particular points. What you say is, in addition to plus this, y goes to minus y. Okay, y goes to minus y. So you identify y minus y to y. Okay, your orbifolding. So imagine that if there is a circle, y is like a circle. This is 0. This is pi r. This is 2 pi r. Okay. Now you are saying further y goes to minus y. So everything, this point is identified with this point is identified with this point is identified. Essentially, you are identifying all the points on the perimeter with the other points on the other half perimeter. So this essentially becomes a line. This just becomes a line or an interval 0. Y is equal to 0 to y plus 2 pi r. So you can take it as a phase essentially. You can just take it as a phase essentially. Now in addition to that, you are saying y is equal to minus y. Y is equal to minus y. Okay. Now, if you take it as a phase or a circle, essentially, this part would be minus y, this part would be plus y. Now, if you are saying y is equal to minus y, every line on every point on this will be identified with the point on this line. So the entire thing can be just mapped into this particular point on this line. So these points, these are called singular points, 0 and pi r. And here 5D Lorentz invariance is broken. 5D Lorentz invariance, you can have 4D Lorentz invariance, and you can use the 4D gamma matrix, gamma phi, to define chiral fermions. Okay. So you start with the idea. Now you can put in, these are called singular points. Now the basic idea is that you have x4 everywhere, essentially x4 everywhere. In the extra dimension, you can put along the line everywhere, you can put an x4. You can put an x4. But what you see, this is a dimension. As you go along the dimension, that means you are going along the energy. You can always give it, say, any length scale. If you are probing, you can probe it as, you can imagine that you are probing it like energy, essentially. Why you can say that? How can you say that? It looks very non-trivial, right? Because it's an extra dimension. First of all, it is like speculation power. My postdoc doc, whenever I used to tell him some idea, he used to tell me, this is speculation power. So he used to tell me that. Okay. Right. So it is somewhat like that. Essentially, you not only have an extra dimension, and then you have an interval, and then you say that this interval, going along the interval, is like going along energy, essentially. Okay. This is true. This happens to be true because there is something, I'll come to that later on. Just believe me for the present. You can do something called the Kaluza-Klein reduction. Essentially, if you have a 5-dimensional field, say for example, it's very simple. Let's just take del mu phi, dagger del mu phi. Now, instead of writing in 4 dimensions, write this in 5 dimensions. Okay, and this field now travels in 5 dimensions. Okay, this field, pardon? Here, in this case, at this particular point, 5-dimensional Lorentz invariance is broken. It's broken to 4-dimensional Lorentz invariance. 5-dimensional Lorentz. Now you break them down to 4-dimensional. Okay, 5-dimensional Lorentz invariance means you can imagine that it's already 5th dimension has a rotational invariance is broken because of the compactness. Okay, you can only have a surface thing, essentially. Okay, a translation is there, essentially, but then it's also broken. Okay, and boosts are also broken because you have boundary. You cannot go to any boost you want, essentially. You had to think in terms of the momentum. Okay, because you have a boundary, you cannot go to any boost you want. Okay. It has become compact, so it breaks many things already. And on the top of it, you put singular points, essentially. So where you identify, because 0 goes to 0 only, pi r goes to pi r, minus pi r, r goes to minus r. So there's nothing. Okay. Yeah, you can just use the phone. Now, what happens is if you write this and say phi of x, y is equal to phi of x mu plus y plus 2 pi r. You use this boundary condition, put it back into the equation of motion. So you get infinite modes, because then you can use a Fourier series of phi. Okay, because this is a periodic function. In phi, you can write phi of x mu of y is equal to some Fourier series n is equal to 0 to infinity e power I n r r n y by r, yes, times some phi tilde of x mu. This is nothing but Kaluza-Kalin reduction. Put it back into this, you get huge tower of states. Essentially, you get huge tower of states. So that means your 5-dimensional theory is equivalent to a 4-dimensional theory with masses increasing 1 by r. Okay, each mode contains 1 by r. 1 by r, 2 by r, 3 by r, 4 by r, 5 by r, and so on. Okay, for a given r, you get what are the masses. R is equal to TeV inverse, you'll get up whatever. So what I tried to argue was that having an extra dimension is having a 4-dimensional theory with increasing in energy, a tower of states with increasing in energy. I'll do it later in greater detail. Okay, but the principal point why we need this entire business is that we have 0 and pi r. There is a boundary in extra dimension. Suppose if we have 5-dimensional fields, which are gauge fields, and you give boundary conditions of those fields such that the boundary conditions violate the gauge symmetry. Okay, such a breaking is called Scherz-Schwarz breaking. It was introduced earlier in string theory, essentially bosonic string theory. So it's called Scherz-Schwarz breaking. You can break the this is equivalent to spontaneously breaking the standard model without having a Higgs. These are momentum states. You write them in terms of momentum states. Okay. This is a scalar. You can do the same thing with a fermion. Here I wrote Klein-Gordon field, but you can do the same thing with okay. Up to infinity, because it goes from 0 to infinity. A mass of new fields, of these new fields, phi tilde fields. Now this field disappears in your Lagrangian. You substitute this back into this Lagrangian, derive the equation of motion. There are multiple fields which are phi tilde n, and the 0 mode, there will be always a 0 mode essentially. That too you got call it as a standard model one, which has 0 mass, and the rest of them are essentially your tower of states. We will do it systematically at some point when we get time to do extra dimensions in great detail, like supersymmetry also, which we did. So the entire point is that suppose if you have a field, say for example, now I put a gauge field, say for example. So I put a gauge field A mu. Now at each vertex, at each singular point, I had to give it a boundary condition essentially. These are all quadratic equations of motion. So I can choose Dirichlet or Neumann boundary conditions essentially. So I can choose mixed boundary conditions also. Okay, Dirichlet is on the field itself. Neumann is on the derivative of the field essentially. Both of them have to be specified essentially. Now if I choose, say for example, sometimes the notation is plus minus. If I choose boundary conditions which are incompatible with the field, it will break the SU2 symmetry. So if I take gauge field essentially, okay, I don't need a Higgs anymore. I don't need a Higgs anymore. The gauge symmetry is broken. This is equivalent to spontaneously breaking. You can show that it is equivalent to spontaneous symmetry breaking essentially by choosing your boundary conditions in such a way. There are 4 choices of boundary conditions. Like I said, Dirichlet, Neumann, Neumann, and Neumann, Dirichlet, mixed boundary conditions essentially. Choosing them, you can show that you don't need a Higgs at all. And you can break the thing, the SU2 cross U1 essentially. Now, typically they didn't even put fermions. There is a paper on trying to put fermions on interval, which is very hard. Okay, Grosjean and company, Shaki, Grosjean and company, there is a paper. But typically you just see how the gauge fields propagate essentially on this interval. Choose the boundary conditions, okay, and see if it satisfies the electroweak precision test. Because the biggest constraint on all extra dimensional model comes from electroweak precision test. Okay, so if you somehow satisfy the electroweak precision test, your model works. Higgsless model. Yes, you're saying. In the bulk also. Yeah. No, it'll map to, okay. Right now we are not worried about. We are saying that okay, we are not putting any brain or anything essentially. Okay, we will map the energy according to what the phenomenology tells. Essentially. So what matters in this is not this one. The strongest constraint comes from the lowest first KK mode. When you expand this in terms of this, you can also work in 5-dimensional fields. What appears is the corrections to the S and T parameter. This one, the 0 mode is essentially standard model. The first mode will contain the corrections to all the phenomenology. So where is the first mode scale is the important thing. Okay, so you break this, and then now gauge fields, you know that at one loop you can work this the entire thing, have very strong constraints coming from electroweak precision test. So you can write this entire thing in terms of 5-dimensional fields also, or you can work with the standard 4-dimensional fields. If you write it in terms of 4-dimensional fields, you will have corrections coming from KK1. Corrections coming from KK1 on all possible electroweak precision test. You don't even forget about putting electroweak, meaning putting fermions and building the entire standard model Likava and everything. Just take the gauge sector and see if it works or not. This already puts some constraints on MKK1. So the MKK1 in the simplest models should be around 5 TeV or something essentially. Okay, from electroweak precision test essentially. The S parameter. The S parameter is already around 5 TeV or something essentially. Now S parameter, if you remember what it is, S is positive and MKK1 should be around 5 TeV if I remember correctly. It's a pretty large number essentially. So somehow you say that the KK mode is heavy and try to make this work. Okay. It turns out these models are exactly equivalent to Technicolor models. So if you make somehow Technicolor work, even putting in an extra dimension by pushing the KK mass high, what killed it? Why is this model killed? It predicts no Higgs. Okay. 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 This model predicts no Higgs. Okay, that's the problem. Yeah. Pardon? That is a different model. I'll come to that essentially. Okay. Yeah. Yeah. That is still you can make it work with a larger gauge group. Okay. I'll come to that in a second essentially. These are purely Higgsless models. Okay. So, but the only problem is even if you can make the S parameter, there are some variations of it and everything. Make it as parameter. It turns, there is a general prediction. I think I put it in the Teams page. Look at it. There is a general, because I said I'll find some time to talk about the technicolor and everything. I've been promising it, but it's a loose end lying there somewhere. But I'll come to back to it at some later stage, essentially. But it'll be there in the notes. You can just look into it. So all the technicolor models predict S parameter positive, and the Higgsless models also predict it positive. And there are versions of it. Even if you take this extra dimension, not like if you take it warped, even if you take it warped, that means I'll come to that. If you have a cosmological constant and this extra dimension has some curvature, okay, even if this extra dimension has curvature, so there are some ideas that if the extra dimension has curvature, the S parameter can be made negative. Those are called holographic technicolor models. In all these models, the S parameter kills it. Okay, but in the simplest models, we didn't go to holographic models essentially. Even in the simplest models, it turns out the discovery of the Higgs itself is killing it. The Higgsless models, because they predict no Higgs, the Higgsless models, but you find a Higgs, so you cannot say it. They're not equivalent to, they're not completely equivalent to technical. Yeah. They may still work. We will be still working on them. Right? We will be still working on them actually, yes. Right. If we didn't discover the Higgs, yes. Yes, plan B was right. Yes. There are several plan Bs, that's the problem. Okay. Right. So more actually, this is the discovery of the Higgs turned out to be plan B. Okay. Plan A, B, C, D, F, and everything are new particles essentially. And plan Z was discover this nightmare scenario essentially. Okay. Yeah, sometimes I wonder we'll also hit the dead end in dark matter also like that essentially. I fear that. Okay. Yeah. Okay. Somehow the saturation is happening very fast. Yeah. So then there is a variation of these models where there is a Higgs, but its mass is predicted by extra dimension. These are called, these are models which he was mentioning essentially. There is a very nice set of by Raman Sundaram which talks about this. Yeah. It is predicted, no? It is predicted to be less than 135 JeV. And set a limit, but upper bound. So it is found below that. So it means Susie is correct. Has to be correct, but assuming that the stops should also be around 1 TeV or something. But we didn't find any rest. See, that is the reason why people are still working on Susie. Okay, because there is still hope. Okay, yeah, right. No, in principle, yes, but these are very heavy. Okay, in principle, yes, very small. I mean, imagine that you had to produce, these are not valence, they had to be produced in C. So, but they're 1 TeV. So their distribution falls off e power minus m some energy scale essentially. So they're extremely small essentially. Okay. So this is a very nice set of lectures. Um, I think when he was here, I think I spent most of the time talking to him only on the Stasi lectures rather than other things. But okay, this was called from fifth dimension and back. It's a very nice set of lectures. So there is this uh, mechanism called Hosotoni mechanism, and okay, um, which by Japanese. Now the basic idea is that if you have a 5-dimensional gauge field, this can be decomposed into okay, maybe I'll write it down simplerly. A mu and F5. This being the scalar particle essentially. Now typically there are gauges in which you can set other partners to be in, if you start with F mu essentially you can set the other partners to be 0 and you can choose a gauge and everything essentially. But the point is the moment you have um, the mechanism previously which we did breaking with boundary conditions is called Schwartz mechanism. Okay, Schwartz mechanism. Now instead of setting, you use the same Schwartz mechanism, but now you identify the fifth dimension of the gauge field, okay, the field T, to be the Higgs, essentially. Okay, the fifth dimension now Sundaram, okay, you can do it with SU2 and everything essentially. What Sundaram does it, just does it with U1. Just does it in with simple U1 and he calculates the entire thing essentially. It is quite detailed essentially. The basic idea is that the Higgs mass also can be protected here, is protected, but what is protecting the Higgs mass here is the gauge symmetry itself, because it's part of the gauge multiplet. Okay. No, U1 essentially means here it's an example with U1, but you can do it with SU2 and U cross U1 also, but it is done in SU2 cross U1 also essentially. There's no problem. Khosatani has still writing papers on it essentially with SO10, SO5. Every day he writes one paper, so you can see it. Okay, right. So hope this it's not recorded and nobody sees this. Okay, I should be very careful essentially. Okay, but I know. Yeah, yeah. So what happens in this case is that when you do the Kaluza-Klein reduction and everything, and choose a gauge choice and everything, this fifth dimension part, the scalar part, can develop a potential. And this potential is also has one loop corrections, has one loop a la Coleman and Weinberg, essentially. Coleman-Weinberg potential. So you can define something called the Coleman-Weinberg potential. So you can have a V effective sum m power 4 log m power 4 m square log m square trace of this mass matrices by q square, some form of this particular. Yeah, something like this. Okay. Okay. The form will be roughly like this essentially. So it goes as fourth power in the mass essentially, fourth power in the mass log of m square by q square essentially, the Coleman-Weinberg. This form is well known. But then what are the masses which appear here? What are the masses? It will be the full Kaluza-Klein tower. Okay, it will be the full Kaluza-Klein tower which will appear here essentially. And then if you take the double derivative with respect to the Higgs, it gives you the Higgs mass. All of the masses will appear here. And the sum is up to the infinity. Okay, and those sums cannot be done. They are not convergent, they are divergent essentially. Those sums, these are somewhat similar to the Jacobi sums which Justin does, and also Anant also is doing nowadays. All these Jacobi things. Okay, so these are all just Jacobi sums essentially, which you have to do. So you typically cut it off essentially, if you are unable to form a closed form essentially. Okay, and get this form essentially Coleman-Weinberg potential. So and then you say that okay, there is a symmetry which protects the Higgs mass. I can calculate the Higgs mass from this particular model and everything, but then it requires in the loops some Kaluza-Klein models, gauge partners, which are either W1s or W2s or Z1s or Z2s, some heavier gauge partners which are required. Did we find them? No. No. So we didn't find any heavier gauge partners. These are also roughly around a TeV essentially. Okay. So instead of using supersymmetry to protect the Higgs mass, you are using the gauge symmetry itself. It's a fantastic idea. It's a beautiful idea, but it requires some heavier gauge partners into your theory. Pardon? Yeah. Okay, if you put in a global analysis, putting electroweak precision test and all that kind of things, it be pushed up a little bit. And then you will say it is not expected at LHC. Okay, okay. That's what happens in extra dimensions actually. If you put in all electroweak precision test and everything, in most of the models, the scale is pushed beyond the scale of LHC. The minimum scale is around more than 3 TeV or 4 TeV, I think. We had the latest, after the Higgs discovery, we had an analysis. Yeah, I and Sridhar and Abhishek did it, and we showed it is beyond LHC. Okay, we didn't say it explicitly, of course. We said that probably could be discovered at LHC, but it's obviously it cannot be seen at LHC. We cannot write a negative statement in the paper. You see, you had to be positive. So, yeah, it was obvious. So this is a beautiful idea. So, but it also expects some partners. And if you do a global analysis, putting electroweak precision test and everything, it pushes out of reach of LHC. Out of reach of LHC. Now, the problem with particle physics is we had to be pragmatic. We are constrained by experiments. Suppose if you are a string theorist, forget about LHC, we'll build something else or whatever it is, and we can okay not bother about it. Essentially, we don't care what mathematics is tells you is the ultimate. So that's what we will live with it. Essentially, we could have gone that philosophy. The calculation is a calculation. We can do the calculation. So that's a beautiful idea. It works. Finished, published. Nothing right assumption. Right. Okay. But unfortunately, we have to worry whether it is in reach of LHC or not in reach of LHC. Okay. These are the main constraints. The experiments are very big, very, very constraining actually. It's not a good thing actually. We should okay. Yeah. Okay. So no, no, the heavier. No, the heavy, they are there already, but the scale is not fixed by the theory. The scale is fixed by the experiments, either relative precision test or your direct searches at LHC. Anything, anything. SU2 cross SU2, SU3 cross SU2 cross U1. If you put this thing, this entire thing works. Theory wise, it entire thing works. Everything works out. But then you have to worry about the electroweak precision test. Okay, electroweak precision test, because the Higgs is a part of the gauge boson loop, essentially everything. So everything gets tied up. Same like the corrections which give you mass to the Higgs also correct that zero mode gauge bosons. Okay. Hmm. And gluons, you don't make them partner. Yeah, WZ. They are partners of SU2 in 5 dimensions. Okay. Actually, if you want to make everything work, you have to take something like SU5 or SU10 or something. Okay. So you have to have a larger group. They are partners of that. The Higgs, you can identify it. SU2 cross U1 also, it has been identified, and it has been shown that this calculation is finite. There are no quadratic divergences, nothing, because the gauge symmetry protects it. The group tells you what is the thing. No, 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 there are no extra. Just let's take standard model gauge group. But then you put it in a bulk, in a extra dimension, which in a bulk. The zero modes are essentially a standard model gauge bosons. But then you have the heavier modes, all the heavier modes, because of the Kaluza-Klein tower. The same thing which I showed also works for uh, gauge boson equation of motion, right? Essentially, F mu also, if you take, okay, and you write express a mu in terms of some series of, because it also has to go back to itself in extra dimension. So a mu also you have to put the Kaluza-Klein thing. These are excitations. These are excitations of it. So these partners which I meant for the gauge partners are excitations of the KK tower. Excitations of the KK tower. So they are not found. KK1 and everything. So, okay, now let's the so the best thing which seems to be working as far as, because we are really worried about the Higgs, is composite Higgs models. Okay, there are other models of extra dimension. Okay, maybe I'll just mention Randall Sundaram also, just to, for completeness sake. These are a little bit more complicated. this doesn't directly have per se the Higgs effect, but we showed that it has an Higgs effect essentially, because in the moment we put in Higgs, it turns out that it put constraints on, from STU parameter, it puts constraints on the lightest KK mass, light KK gluon, KK gluon, KK gluon, and the KKW. They put constraints. The KK gluon is significantly constrained. So there are various ways in which. So this is also this is typically called orbifold model. Again, same thing. S1 by Z2, which I said Z2 is y goes to minus y. Okay, S1 is a circle. This is the circle. This is the Z2. This is Z2. S1 is a circle. Okay, the biggest thing, this metric is not 5-dimensional metric, which is not factorizable. So far we have taken eta mm 5 dimensions, dv eta mu nu, okay, 4 dimensions, and 1. All the extra dimensional models which we are considering. Okay, in the Randall-Sundram model, if you solve for the Einstein's equations of 5 dimension, it has GR effects essentially, in a way, because it considers something called the non-factorizable metric. Okay, you cannot compose it in this particular fraction, so it's a non-factor. And in other words, the reason is it is a solution of the Einstein's equations in which there is a cosmological constant, a huge negative cosmological constant. It's an antidetectable space. Okay, so huge negative solution of Einstein's equations with minus lambda, and minus lambda is pretty large. Okay, and you put this, and so the fifth dimension, the 4 dimensions are affected by the way the fifth dimension propagates. Okay, as y moves, the 4 dimension is also affected essentially, the way we see the 4 dimensions. Okay, it's antidetector space, ADS space. So that is the reason why we people will believe that ADS CFT also holds for Randall-Sundram. Okay, and the metric is given by ds square e power minus 2k pi eta mu dx square minus dy square or d phi square. There should be some r square difference. You see, I have written it as r phi, or okay, r phi or k phi. Okay, so this so dx square, okay, the dimension 4 will have a component of the fifth dimension sitting in it. Okay, so it is non-factorizable. You cannot factorize the 4 dimensions and fifth dimension separately, whereas the earlier ones you can factorize this and this completely. Okay, this is called non-factorizable. So this is typically represented in this particular fashion, and then it doesn't stop. This solution is not just with this. Essentially, it also assumes that there are some large D brains, are also called domain walls or something in field theory. Essentially, there are some domain walls sitting here and there at y is equal to 0 and y is equal to pi r. Y is equal to 0 with some tension, and only when you put these tensions and everything, factorize it, you get this metric. Okay, putting conditions on these tensions and everything, you get this metric. You can solve this essentially. Okay. No, they are different domain walls. It's very important. Actually. There are two different domain walls, and there is only gravity in between, and with a large cosmological constant, negative cosmological. So one of the brains you call them as the standard model brain, or other brain you call the Planck brain. Sometimes you also call it as the TeV brain and the Planck brain. So when you solve just graviton equations of motion, essentially Einstein's equations, and solve for the graviton equations of motion, you see that graviton couplings to matter are much weaker here in the TeV brain, whereas they become very, very strong when you go to the Planck brain, which is as expected. It tells you why gravity is weak in 4 dimensions, but it is very, very strong when you go to Planck scale. So that is the reason why this model is so famous. It gives you a physical picture explaining why the gravitational interactions are the weakest interactions. Okay. So these Randall syndrome models are popular also in string theory. They are many this kind of solutions. They have important, and one of the main things is to get these models directly from string theory. So people have been trying. There are some no-go theorems telling that it's not possible in string theory. There are some things which tell you there is something. There are some solutions called throat solutions, Klebanov, Strassler, Strauss, and everything. But nowadays nobody is doing string theory. So they're doing something else. But there are these Klebanov, Strassler, Strauss solutions which also look something similar to this. Okay, they look something similar. So yeah, there are these questions whether you can get it from string theory or not. And it's also a question of the scales, essentially, whether you get the scales right. And pardon? Brains are solutions of string theory, essentially. So these we think in terms of field theory, not in terms of string theory. We just think in terms of objects which are like solitons or domain walls or something, which are occupied in large sections of space time, which are localized in large sections of space time. A bound of energy localized in a solution which is a bound of energy which is localized in space. Classical solution. Okay. Solution. Okay. Yes. You assume these classical solutions on those geometries. You are placing them explicitly. Now, you raised an important question whether they will be stable. Will these solutions, the brains also will fluctuate because these are wave solutions, right? Essentially. So, to stabilize them, you need to put something else between in the bulk. You need to put a scalar field with particular interactions, which is called the Goldberger-Weiss solution, essentially. So, you do all that, essentially. So, Randall syndrome plus Goldberger-Weiss and everything, and that gives you negative interactions. So it gives you some sort of negative gravity which balances, because if you leave them, because these are brains with opposite tensions, they'll attract each other, and gravity is always an attractive force, and they'll eventually fall off with on each other, and this entire setup is gone. There is no radial distance and everything. Okay, so this is not a stable radius essentially under gravity, so things can fall off, and then this, to make it stable, you need to put in some extra fields in the bulk. And pardon? Which side? There is Planck brain, and this is only the setup S1 but now in between you can put a lot of brains if you want. If you have 6 dimensions, okay, you have solutions. You can put one more brain there. In between, this is a Planck brain, this is a standard model brain. There's nothing else in between. You can put that will it make it stable? That's the question essentially. That's the question you are asking. Oh, okay. So if you but the point is the brains are will only attract with each other. So you need something which acts with repelling force against the gravity. So you need to put a scalar field with a potential which will repel this gravitational force, which will repel. So you had those that scalar field should be a part of the energy momentum tensor of your result. So it puts in some energy which goes in the negative direction of the attractive energy of the gravitation. Yeah, I don't know if you change the tensions of the brain whether it will become stable or not. You are worried about if there is some configuration in the extra dimension which somehow makes it stable. Um, if you have 6 dimensions, there are some configurations because it's now not a line but a square. So there are some configurations people have looked at. Soumitra Sen Gupta and company, they claim that there are some configurations which are stable. Okay. I don't remember. I worked a little bit on 6 dimensional physics, but long time ago. Now I don't remember. But there are some configurations which could be stable. But without putting the scalar field also stable, I don't remember that part. Kenji Nishiwaki in Shivnadar and his collaborators have been looking at putting a lot of brains in between. And I don't remember how they stabilize. I know that he has 3 brain configuration and everything. There is a paper by Sundaram on effective field theory of 3 brain configuration. Long before, okay, okay, yeah, it could be a new skill, or you can push this here. No, what is the problem? Okay. Now what happens in this case? Now there are several choices. You can put the standard model Higgs here. Okay, just localize it here. So if you put the standard model Higgs here, the constraints are very significant from STU parameters. Puts the constraint on MKK, the generic KK mass, to be greater than 22 GeV, 22 TeV or so, 20 to 30 TeV. Okay, so huge, meaning you cannot make it work at any scale. If you localize the Higgs at the IR brain. Okay, I should also tell it's also called UV brain, and this is called IR brain. I'm giving you snippets, very fast snippets of several models. Yeah, right. Yeah, okay. This the constraints are about empty. So forget about Higgs and everything. This is LHC and everything. Now you can make this as a in the bulk. Higgs propagates in the bulk. Then even then the lowest we can get from STU parameters is 3T. With custodial symmetry, there is something called plus custodial symmetry. And most of this custodial symmetric RS have top partners which are uh, top like colored. Okay, they have top partners, and these top partners have constraints. They contribute again to electroequation test, and they are not found. Now you can escape by saying that, oh, they are not expected to be found at LHC because their masses are supposed to be heavy. Okay, their masses are supposed to be heavy. So if they are not, so the electroequation test also for the top partners, top prime, is also around T. So this is 3 TeV, 4 TeV, 3 to 4 TeV is just beyond the reach of LHC, because imagine that LHC has root as about 14 TeV. So you won't be able to produce it. Take 7 TeV. So if you want to pair produce, it will be maximum pair producing each. So if you distribute 7 TeV along 3 blobs, say 3 quarks, roughly around 2 TeV. So root S would be maximum 4 TeV. 3 to 4 TeV particles are very hard to be produced at LHC. Their production cross sections are very low. Okay, and kinematically they are extremely hard to be produced. So you say that they are beyond reach of LHC, and they predict the nightmare scenario essentially in principle. Okay, they predict the nightmare scenario. Okay, so I'll stop here. Okay, yeah. So what we discussed are essentially the nightmare scenarios. Okay, I tried to convince you that all this is the motivation to do what next. Okay, so what next is effective field theory. Okay, if the scale of the physics is very high, how will you deal with it? So in the next class onwards, we'll start doing with effective field theories, and at some point we'll come back to these models in more greater detail. Essentially, okay. There is also composite Higgs, which I'll do it later on. Okay, any questions?